Howdy folks, and welcome to part 5 of my electrical age tutorial series. Today we're exploring how to regulate your power systems so you can leave them alone safely. Now the first thing we're going to go over is the two types of regulation. You can have both internal and external furnace regulation. For internal furnace regulation, you have three options. You can have an analog power regulator, a 10% digital power regulator, or a 1% digital power regulator. Now the analog power regulator, when you put it in the slot, is going to adjust your power output gauge from the furnace so your temperature is equal to whatever you set it to. Right now I have my temperature gauge set to have a target of 300 degrees Celsius, so the analog regulator is going to adjust the control power gauge until the temperature reaches 300 Celsius. As you can see, as our consumption is constant and our generation is constant, our voltage is constant. Over here, we have a 10% digital power regulator. Now, it's called 10% digital because when your current temperature is 10% greater than your target temperature, it turns the furnace off all the way. And when your current temperature is 10% less than your target temperature, it turns the furnace on all the way. This is helpful in that your furnace doesn't run constantly, so it's not using a constant amount of coal. The downside is that because it doesn't run constantly, your voltage is going to vary, simply because your power output is going to vary. Note that you can also put regulators in furnaces. By regulating the temperature, you can actually make your furnace use less power than it normally would. This core is rated for 150 watts, but currently he's only drawing 125 because he doesn't need that much. Your final type of internal regulation is the 1% digital power regulator. This guy is similar to the 10%, except it's a 1% difference that causes him to turn on and off. The one difference between this unit and the previous two is that the signal box on the ceiling is going to cause this electrical furnace to turn on and off every 30 seconds. Since he's not regulated, he's going to try and draw as much power as he can. This effectively makes this little circuit here a variable load one, and as you can expect, the voltage is also going to vary. This is the downside when using internal regulation, in that you can't account for the voltage on the cables. If you don't make this regulation and set it up really carefully, you can easily have an overvoltage on your cables and an explosion. On the other hand, it's extremely cheap compared to other regulation methods, so if it's for something like charging batteries or high amounts of power generation that you know is going to be a constant load, it's probably a better idea. For smaller things and bases and more residential type stuff, I recommend external regulation. Now, if you set stone heat furnaces to external control, and you put a signal cable on the side of them, whatever level that signal cable is going to be whatever level its power output gauge is. So right now, the gauge is at 56%, which means the signal is at 56%. Note also that stone heat furnaces transmit signal levels through the furnace. So not only is this one getting a signal, that one's getting a signal, and however many more you want to put in that direction will get a signal. Now the question you have to ask yourself when regulating externally is, where do I want to take my voltage measurements? You can take them at the power generation source, or you can take them over at the consumption area. Now the two differences between these are obviously going to be what voltage and power you get. As we've seen time and time again, the longer your cable length, the more voltage and power you're going to lose to cable losses. So, right here you can actually switch whichever one of these it activates. Right now it's reading regulations and causing the turbine voltage to be between 50 and 55 volts. If I switch it to regulate from the furnace side, you can see the power consumption, or production as well, is going to go up. This is because it's telling it to be from 50 to 55 volts here at the end of the line versus at the beginning. So for it to be 50 to 55 volts here, you actually have to produce more power to overcome cable losses. Now, this might be good in terms of fine-tuning devices and making sure you get exactly the amount of power you want at your locations of your components, but you have to remember that if it's between 50 to 55 volts here, it has to be at least 50 volts or greater here, or at least 55 volts or greater here, simply because it has to have a higher voltage and higher power here to make up for those cable losses. This can be problematic if you run long cables and take measurements in the end, and that you can actually cause too high of a voltage to go over here, and you can explode your systems. So I really recommend just taking a voltage reading off your turbines and sending it back into your stone heat furnaces. Now you can regulate things other than just your turbines and stuff in power systems. In fact, you can regulate most anything in electrical age. Right here is a roof power system that regulates, again, most everything about it. And yet, you can imagine it's kind of complicated. But if you take it one piece at a time and break it down, all the regulation is actually pretty simple. Let's start with the easiest part of regulation to understand: temperature and power on cables. Now this probe right here is set to measure the power on this cable and varies between 0 to 1500 watts. Now the power going through this cable is also going to be the power going into the turbine. This guy here measures the temperature on that cable, which ranges from 0 to 800 degrees. The temperature on this cable is going to be the temperature going into this turbine. And obviously we really don't want our temperature of that turbine to be greater than 800 degrees. Similarly at the end, this guy measures the temperature between 0 to 200 degrees Celsius and sends it to this little wireless guy, which is going to send him over there to the control room. This guy here does a similar thing, except his value is from 0 to 100 degrees Celsius. Now it's because of this, simply because it's easier for me to write out equations with stuff that's 0 to 100 than 0 to 200. But it can be whatever value you want. The reason it's that way is because these fans have a Tmax of 150 degrees Celsius, but their nominal operating temperature is only 50 degrees Celsius. So if they get hotter than 50 degrees Celsius, you want to start providing power to them to turn them on. Again, active coolers have an inherent cooling value, which right there is 200 watts. So if you're only giving them 150 watts, you actually don't need to run them. This little signal box here is used to control whether or not this circuit's open or closed, and whether or not the fans are going to get power. Right now it's using an RS equation, which is reset, set, or basically turn off and turn on. That relay is going to close, and power is going to go to those fans when A is greater than 0.5, which is this cable. And since A varies from a temperature between 0 to 100 degrees, half of that's going to be 50, so when A is greater than 50 degrees, close the relay and let power flow through, which will turn the fans on, which is what we want. Now you also want them to turn off after they've been cooled enough, so I say when A is less than 0.4, or when the fan is cooler than 40 degrees, turn it off, so we don't waste power cooling things we don't need to. This will have a slight reduction in efficiency of our turbines, since it won't be as cool, but I believe you can also make up for it, and the fact is if your load is highly variable, and you really don't need the turbines for half of the time, then it's probably better to have this on, so you don't run them all the time and you don't consume that much power. Moving over here to this section, this guy here is simply going to read the power off this cable, and it's going to be 0 to 150 watts, simply because the coolers don't take that much power. This guy is simply for reading power outputs, and he's going to go over to the control room. This turbine is hooked up in a way similar to the other turbines we've seen, except one key difference is needed to remember, and that we want this to run on and off, not based on the voltage of this cable, or anything about this circuit, we want to turn on and off based on the temperature of those coolers. That means our signal equation in this box is going to have to be revised a bit. Now first off, this probe here is going to read the voltage on this cable between 200 and 250. Obviously, for safety's sake, we don't want the voltage to go too high on this cable, no matter what the temperature is. If it goes to 260, it's going to explode, and then that's not going to get cooled, and it's going to explode again. So there are some inherent safety things. Again, this is a wireless transmitter, so that's going back there to the control room. This guy here is a receiver. And what he does is he receives the temperature of those fans, which is a key to determining whether or not we want this guy to be on or off. Now he comes in on the red side. In the equation, he's A. Also note that that's F2 fan FT, which is going to be this guy right here, which ranges from 0 to 200. Obviously, we never want these to be at 200, and if they are, they've probably already been blown up, so we have to take that into account. Right now, I say is take A, multiply it by 2. If that's less than 0.4, then turn it off. Otherwise, A times 2 is greater than 0.5. Turn it on. This equation part right here is actually identical to the one right here. The only reason he's multiplied by 2 is because that thermal probe reads from 0 to 200, and that one reads from 0 to 100. So he's going to turn on and off and sync with the opening and closing of that gate. These two sections here deal with how much power you want to output. Now this guy here is the C side, which is going to be the voltage. And that obviously we don't want the voltage to get too high. So if 1 minus C, and C reads from 200 to 250, so if C is 100%, that's bad, which means 1 minus 100%, or 1 minus 1 is going to be 0 times 0 times 0, that's going to shut it off. So the closer the voltage gets to 250, the lower this value is going to be, and the less power your furnace is going to produce, so your voltage is lower, and it doesn't explode. Conversely, the higher the temperature is on this thing, the more power we want to produce. So with the temperature coming in slot A, basically I multiply it by 4. And this can be whatever you want it to be, I just picked 4. So if temperature is really, really hot, but your voltage tells it to be, oh, you're close to 250, start shutting down, this is going to be a relatively small number. On the other hand, if your voltage is like 200 and is pretty big, and your temperature is pretty low, it's going to say, hey, you don't need to have that much power coming out of it. We're not that hot in our fans. Make it smaller, produce less power. The key to multiplying these comes in is if your voltage is about average, but all of a sudden your temperature spikes. Then that's going to be about 50. That might be 0.75 or something, and that's going to get larger and cause your furnace to start cooling more. Again, all these coefficients like this 0.1 and this 4 here are up to you and your demands. But the neat thing is that you can actually say, only cool this when it needs to be cooled, but do it efficiently. Now another section over here is for the power generation system. Now this guy, obviously we're putting stuff in here, and these probes are the traditional measure a power off a cable and measure a voltage off a cable. Now as we saw back in the tutorial dealing with power systems, or tutorial 4, you can put stuff in a box and cause it to generate power efficiently, which is what we've done here. Again, this is A is greater than 0.6, turn it off, or if A is less than 0.4, turn it on. Now A, again, is the red one, is going to be our voltage, which 0 is at 200 volts, and 100 at 250. So, if A is greater than 0.6, or if A is greater than 230, or voltage is greater than 230, turn it off, so we don't overvolt the cable and explode it. If your voltage is less than 220, turn it on, so we've generated enough power to keep it at that voltage. And obviously our B is going to be our power cable here, which is set to keep the power between 1100 and 900 watts. Pretty simple. And again, this guy's another transmitter that sends it to the control room. Same thing with that guy. Now this junction box here is a unique twist, in that he has an if statement. So, if C, use B, otherwise use A to control your furnace. So if C, and this is simply a relay to the override switch, so if the override switch is on, control the furnace using this box. If the override switch is off, control the furnace as we normally would. Now this box takes in the voltage off the turbine and the voltage specified in the override thing in the control room, and does some math on them, which is kind of complicated, but in the essence it makes sure that your voltage stays in the range of that override switch. So you can actually use this to manually control your voltage, which we'll do in a little bit. Another thing you can do with regulators is control your load. Here you have a bunch of signal boxes hooked up to these little wireless receivers, and in essence this is hooked up to a signal trimmer, which can vary its output between 0 and 100%. So here it says if the signal trimmer is greater than 0.2 or 20%, turn on this furnace. If it's greater than 0.4, turn on this one. 0.6, turn on that one. 0.8, turn on that one. You can also do this with other things such as macerators or auto miners or a whole bunch of other things. And you can hook up one of these voltage probes to all these little signal boxes and basically control how many of your auto miners are running so you don't suck up too much power. The last thing in this room is a simple relay that turns on and off the batteries up there. So let's go into the control room and see how it all comes together. Now right now, the system load is set to 0 watts. So obviously the voltage is going to remain pretty constant, no power is going to need to be outputted, and everything's pretty cool right now at about 20 degrees. Now if I go and turn the system load to say 12%, which should turn it to 400 watts. My bad. That should actually be 20%. There we are. Now it's at 400 watts. You can see our voltage dip down real quick. And our turbines are currently spinning up. Now that we've got some power being output, that voltage is going to climb back up and reach the nominal voltage that we set for it in that signal box. Obviously also, because our power output is going to be so low, we don't need to run those coolers, simply because they don't get hot enough, as you can see over here in the cooler temp section. The turbine is also temperature is fluctuating, because obviously they're not running all the time. So when they're running, they heat up, and when they're not running, they cool down. This middle guy here is an interesting graph. It's basically the efficiency of a turbine. Now the efficiency of a heat engine, using thermodynamic principles, is really the ratio of power you get out over the power you put in. Now the reason he's at 100% is because when the turbine switches off, there's actually a little bit of heat left inside the furnace and turbine system that allows it to continue to produce power for a little bit. At that point, you're not actually using any power from the stone heat furnace because it's cut off, but there's a little bit left inside the turbine that's producing a little bit of power. This is also going to result in a little bit of a voltage hop, once you turn everything off, and that your voltage will still increase for a little bit. This is actually a good thing, in that if you make your range of voltage narrow enough, you can effectively overshoot your cap. So say you want your cable to be between 200 and 250 volts. That's a bad example. Let's do 200 and 230 for safety's sake. If you tell it to shut off at about and reduce power, the higher it gets to 230, it's going to reduce it enough that you never reach 230. If, however, you really wanted your voltage to be 225, and you regulate your system between 223 and 227, and all of a sudden it produces a bunch of power, hits 223, starts winding down, and then hits 227, because of that extra amount of heat left in the furnace, you're going to overshoot that 227, and with the way the voltage regulators work, it will actually cut off all power to that system, effectively eliminating that section where you have your furnaces running constantly. I think it's a little glitch in the mod in the fact that your furnaces really shouldn't be running even if you don't have any load on them, but it's just something that we have to put up with. Anyways, as you can see right now, those coolers have actually just turned on because our temperature has gone over 50 degrees Celsius. And now that they've cooled enough, they've turned off. So, let's kick this up a little bit. Say 800 watts. As you can see, once again, we're going to cause a voltage drop, but this time, since the turbines are running, they recover quicker. Our power output is still easily attainable because those turbines can produce 1,000 watts. Although our turbine efficiency has hopped up to about an average of 50%, simply because we're not turning the turbines on and off anymore. And of course, our cooler temps are going to still stay in a good range because our cooler power is going to work out well. Note, though, that the coolers are having to run longer simply because more heat is coming into them through the turbines and everything. Now, what happens if we take this system up and make the load higher than what our turbines can produce? Let's say 1200. Again, we're going to get a voltage drop. And also notice that there's a bit of a power drop. The key thing to remember here, though, is you're not going to actually end up with explosions in this case, unlike you would if you'd used other regulators, simply because our system is regulated well. Our turbines won't overheat, and actually they're getting cooler because we're sucking too much power out. Our fans won't overheat because we've regulated them to cool down if it gets too hot. And we can't have too much power on the cables, or voltage on the cables, because that's being regulated. Now, you want to keep in mind, in this case, our furnace is geared to be efficient. So he's actually not going to run at 100%. This is the reason of the override switch here, and that you can force your furnace to be less efficient if you simply regulate by voltage and not by that power. So this furnace override voltage switch sets the voltage between 200 and 250. I want my voltage back at 225, so if I kick that on, it's going to keep on producing more power, as you can see, to get that voltage up to 225. Note, though, that this will also cause a little bit of a decrease in our turbine efficiency, but not too much. Eventually, our voltage output is going to get up there, right there, where we can see it. So, depending if you're going to be running your system to its limits, you might want to consider switching to a purely voltage-regulated system, instead of having that little turbine coefficient in there. But I recommend not running your system to its fullest, as that puts extra stress on it. That doesn't need to happen. Now, also a thing with regulating systems is you don't have to worry about using too much power or having too high of a load. If I increase this to the full, or 1600 watts, it's not really going to do anything bad on the system. Sure, my voltage is going to drop, and my power output's going to go down, but because it's regulated correctly, our temperatures are going to be fine. We're not going to overvoltage the cables, and we're not overpowering them. So really, we're just not having enough power in general. The converse of this is if the furnace's load is too low. If I was to say give it a 400 watt load and then say keep it at 240 volts, that would cause it to explode. So when regulating, you have to be double sure that you don't ever reach that maximum voltage. I actually had that happen once with the cooling system, and that I wanted my voltage to be 54 volts. So I told it to keep it between 0 and 54 volts. Now these guys had combustion chamber upgrades, and so I was using a 50 volt turbine, not a 200 volt turbine, and that was 200 watts, or 2000 watts, which came out to be about 1500 watts. 50 volt turbine's nominal power output was 300 watts, so I had about 1000 watts going into my coolers, and with the 50 volt coolers, it just couldn't keep up. So that got hotter, it couldn't get that 53 volts, yet it kept on telling it to produce power, and it exploded. Now normally you wouldn't have to worry about that, but just make sure that you don't try and use your systems more than you can use them for. So when it comes to generating power systems, as we talked in tutorial 4, know your loads. That's about it for regulation. Most of it just depends on what you want to do with it and how you want to set it up. Shoot, you can set it up like this guy, where these little guys go on if you ever exceed one of these safe values. You can also engage batteries with regulation, and that, if I was to increase that to the 1600 watts, turn on my override, obviously I can't reach that demand, but with batteries, you can. Again, I don't recommend using batteries solely for this, but as we talked about before, you can use them for temporary times when you need to get a bit more power. And they actually work quite well in the system of regulations. So, they actually don't really need any regulation. Something that can be kind of different if you're doing a smaller system, like we did in tutorial 4, where batteries are your primary source of power. Well folks, that's about it for this tutorial. I don't think there's much more we can explain for the basics of power, but if there is, you'll be sure to hear about it. This has been Ben Plotz, signing off.